The last speaker is Victor Iwaniack, who's going to talk about the two-way automata and the three automata as functors. Well, please go ahead.
Thank you, Paolo. So indeed, this subject I want to present to you is kind of experimental. Actually, I did it like in the last section of my thesis, which I defended a few months ago. I think there are nice examples. And yeah, I wanted also to do a little disclaimer. I'm not in Nice anymore. I will be in Marseille like next month. But anyway, so just to go into the subject, there is two main themes, which are like automata. So I will introduce the subject and the functorial point of view. So let's get started. So first of all, what is an automaton? Basically, it's like a formal machine meant to recognize word with a simple procedure. So a word is simply a finite sequence of symbols. We put them in an alphabet. It's just any set. And so there are elements of the free monoid sigma star. We will use sigma to denote the alphabet throughout the talk. And an automaton, a complete deterministic automaton, is a machine given by a set of states, an initial state, a subset of accepting states, so there can be several, and a way to go from a state to another according to a letter. So basically, if you take all the component, what you get is basically like a labeled graph with some more information. And you can take this little automaton I draw as an example. So you have a unique initial state. You have a unique terminal state, but you could have many or no terminal / accepting states. And then, as you can see, you can go from I to T by reading A, for instance. So I said they were meant to recognize word. So let's see how it works. Well, each time you take a word, you draw a path in your graph. And so, for example, if you take the word Baba, you go from I to S with B, then S to T with A, T to S with B, and finally S to T with A. Okay, so you end up your unique possible path from I, you end up in T, which is an accepting state. So the word would be accepted. This is the procedure. On the contrary, if you take Bab, for example, well, you end up in S, which is non-accepting. So the word is rejected. So basically, as you can see, we have a set of states, some information, but the most important one is like an action of letters and therefore an action of the free monoids on the set of states Q. And this is the basic beginning of the functorial point of view from Thomas Colcombet and Daniela Petrişan. Because you have this classical viewpoint of seeing a monoid or group action as, a functor whose source category is the monoid or the group seen as a single object category. Well, if you take that and you add the information of like the initial and terminal state, you would have all the information you need to describe a complete deterministic automaton. And to do that, you have to see the initial state as a function. So to do so, you just take a singleton and you point out where is the initial state in the set of states. Okay. And most importantly, the way to describe a subset as a function is to use the characteristic function. So we use the fact that like set is the topos basically, and that what I worked on my thesis, it's automata in toposis basically. So as you can see in this quiver, we have all the information of our automaton, and this is like the functorial representation of Colcombet and Petrişan. We take the shape of the quiver, we generate a free category out of it, and then to describe such a quiver is the same thing as taking a functor, and you just require the the leftmost vertex, sorry, to be sent on a terminal object, a singleton, and out to a subobject classifier. Okay, so a two element set. So this free category is very important in the functorial representation, and we will denote it by I sigma star. So this is the equivalence between functors and automata. And one neat thing with that is that you can see how the recognition of words has a restriction of your automaton. How do you do that? Well, you take only the outside, the visible part of the I sigma star category, in and out. And if you take the full subcategory generated by those two objects, then you have a very simple category with two objects, only arrows from in to out, and each row corresponds to a word. Therefore, if you take an automaton as a functor and you restrict it to this full subcategory, the only information you keep is what your automaton send this kind of arrows to. And the automaton sends such an arrow, so a word, to a truth value. And therefore, it tells you if the word is recognized or not. So if you fix a language, it's the same thing as fixing a bipointed functor L. And finding an automaton that recognizes the language L is the same thing as extending, like in a strict way. Okay, so this was like the very basic beginning of this functorial representation. I just want to add one little thing is the fact that I talked about deterministic automata, but we can relax this kind of constraint to get non-deterministic automata. And the difference is basically you have almost deterministic automaton, but instead of a single initial state, you have several or no, so a subset of initial states. And your transition function is replaced by a transition relation, basically. And you still have a functorial representation. It's also shown by Colcombet and Petrişan. And why does it work? Well, this time, if you take one to be a one-element set, you can encode a subset as a relation from or to a singleton. And therefore, you can see, you can have the information of the initial state and the accepting states here. So we have also this equivalence between bipointed functors and automata. But we have to go into the category of sets and relation instead of the category of sets and functions. Okay, so this was the introduction to put the context. And now the plan will be really simple, but I hope it won't be chaotic. My goal in the talk is to show you two nice examples. Well, I think they are nice, and show you how the functorial approach can help you like prove stuff, basically. And so two sections, first two-way automata, then true automata, but each time definition, the functorial approach and how it works, and then an application. So let's start with two-way automata. So for now, the automaton, they were one way because they were reading the word from left to right. And now we will allow the automaton to go back and forth in the word and then end the reading and decide whether he accepts or not the word. How do we do that? Well, a model of that is you take basically the same data of a non-deterministic automaton, but you ask that you separate your states into positive and negative states. I will explain what it does. Also, I need a constraint. I will explain later, but I need initial and accepting states to be positive. So to explain how it works, let's see a very basic example. It's not really interesting by itself, but it's to understand how it works. So if you take this automaton, you have four states, one initial state, one accepting state. And if you forget about the signs, well, you see that you can only reach like the accepting state if if the word is like 3 A's, okay? But if you take into account the sign, so it's really a two-way automaton, then this automaton, as a two-way automaton, recognize the single letter word A. How does it work? You start at the leftmost side of A, then I, the initial state, is positive, so you read on the right. When you read on the right, you go into the state Q. But the state Q is negative, so you have to read back. But when you read back, you read still A, so you are allowed to go to R. R is positive, so you read to the right. And then you end up in F. And then the word is accepted because you are in an accepting state and the reading head is at the rightmost part of your word, okay? So as you can see, there's a very big difference between the automaton seen as one way or two way. And this is the reason why the functorial representation breaks if we don't do anything. Because if you take like a non-deterministic automaton, you can see how the automaton behaves by just looking at how the letter act on state, and then you compose as relation, okay? So the behavior of the automaton when reading the word W depends on the letter and the composition of relation. This will not work anymore, as we've kind of seen in the example. And in order to bypass this problem, we have to see the automaton as not being in the category of sets and relation, but in another category. This is the category intrel. So I will describe it very explicitly, but it has some nice universal features. So the category intrel, its objects are couples of sets. So basically you have a set, a positive set, a negative set. And the morphism are relation, but they are relation in a kind of twisted way. Because as you can see, this relation goes from A plus A minus to B plus B minus. And the relation goes from A plus B minus to A minus plus B plus, okay? Because plus is the coproduct of set, it's a byproduct in the category of sets and relation. You can decompose into 4 components your relation here. And then we represent more in a nicer way. You'll see later why it's nicer, but in a nicer way, we can represent morphism in these categories as squares like that. So you have relation that that starts out of the two corners, basically. So why is it nice? Because the composition is defined as follows. You take two composable arrows in this category, and you put the squares together, and you have this kind of rectangle. And now what you want is a square with vertices a plus, a minus, c plus, c minus. How do you obtain the relations? Well, you actually take this graph and you take all the possible paths from a corner to another. So for example, if you want to go from a plus to c plus, what you do is you go from a plus to b plus with r plus plus. So you end up here. And now you can loop as many times as you want here. And then you have to go through s plus plus to reach c plus, okay? And this is why the relation here, this component of the composite, is like that, because you have R plus, you have the Kleene star, like the transitive, the reflexive transitive closure of S plus minus R minus plus, and then you end up with R S with S plus plus. Sorry. Another just quick remark: if you go from A plus to A minus, then you have two choices at the beginning. You can directly go from A plus to A minus with R plus minus, or you take a longer path. You go to B plus, B minus, you can go back to B plus, B minus as many times as you want. And then you go back to A minus with R minus minus. And this is why you have a union, because you have a choice of path. And then you have kind of the same formula with the transitive closure, reflexive transitive closure. Okay, and this is the place where you do two-way automata. Because if you don't, then you kind of crash down all the positive states, etc., information of your two-way automaton. And you cannot recall what you read before. So the composition cannot work. And also, if you look at the bottom component, you see that the composition is R then S, and in the bottom component, it's S then R. So you're reading backward. So that's basically the intuition. So let's see how it works with the functorial representation. Well, it works, but not as smoothly and elegantly as in the original article. We have kind of to saturate what happens with letters. So we have to define the action of letters seen as single letters word. So we defined for each letter A, delta A star, to be the relation seen as a morphism of Israel that describes the behavior of the automaton while reading the single letter word A. Then you define the action, like the delta star of a word, by its letters, but now you do the composition in the category Israel. If you do that, it works in the following meaning. You defined abstractly the behavior of the automaton when reading the word whose letter are A1, A2, blah, 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 AN. But the theorem of Birget tells you that it's really the behavior you expecting from the machine, okay? And I'm citing Heinz here because I think he was the first one to understand that what Birget was doing like only in automata theory, if I can say, was actually the composition in this category in Trail. Okay, so now we have enough almost to do the functorial representation, but we have to, as always, add the initial and accepting states. How do we do that? Well, we observe that if we probe with the object 1, 0, which is a singleton, an empty set, an object A plus A minus of Intrel, then what we get is a subset of A plus and what I will call a guardrail, un garde-fou, from A minus to A plus. And this is kind of nice because we have a zero object in the category of relation. So we can ask that this relation is empty, and some morphism like that describe subsets of A plus. And we want to describe subset of A plus because we want to describe initial state subset and the accepting state subset. So here is the representation theorem. Two-way automata correspond surjectively to bipointed functor from I sigma star to int rel, sending both in and out to 1, 0. And we ask that those guardrails are empty because we are not interested in them. So why do I say it's surjective? It's because you have to saturate your delta star of A. You cannot just take delta A, it won't work. So it works, but it's not perfect. An application of this representation is a way to go from like the two-way world to the one-way world, because one question people were thinking about is, are two-way automata more powerful or as powerful as one-way automata? We will see that it's not the case. They are as powerful. I will explain why. If we want to go back to set, so to the deterministic complete world, what we want to do is to kind of probe. It would be the simplest way to probe our automaton with the nice object. Well, it partially works. So if you post-compose your automaton as a functor from I sigma star to int rel by the probing functor out of 1, 0, it partially works, okay? Because we obtain, so here we have no restriction, but we obtain the subobject classifier because there are exactly two morphisms from 1, 0 to 1, 0. But here we have to be a little bit smarter and just to say, well, okay, my initial states, they are actually already a morphism from 1, 0 to q plus q minus. So I can represent it as like a function from a singleton to int rel of 1, 0, q plus q minus, which happens to be the set of relation from 1 plus q minus to q plus. So we have a functor that goes from like categories of a category of two-way automata to a category of one-way complete deterministic automata. And this is called the Shepherdson construction because it looks like the same, but Shepherdson did it with deterministic non-complete automata, but it's the same. And this was also, I have to say, it was inspired to me by Tito and Guyenne. So yeah, I wanted to to say. Okay, so this was application with two-way automata. Now we do tree automata. So tree automata, it's in their name. Instead of working with words, we work with tree. But what I call tree, you can call it term if you're like an algebraist. So we replace our alphabet sigma by a graded alphabet sigma. So we have an arity function. So instead of letters, we have functional symbols of finite arity, basically. And well, we suppose that we have constant, so we can form closed tree, closed term. Otherwise, it does not really make sense to look at it. But this is basically the structure we want to recognize now. What is a tree automaton? Well, the complete name would be like deterministic bottom-up tree automaton, maybe complete deterministic bottom-up tree automaton. It's, as always, a set of states, but now we don't have the action of letter, we have the action of the symbols. And for each symbol, we have a function from Q to the arity of the symbol to Q. And we accompany this data of a subset of accepting states. So to my knowledge, the true automaton, they don't have this nice graphical representation. So I will just give you an example of how you read trees using tree automata. So as an alphabet, take the signature of like Boolean algebra theory. So you have true, false, both constants, nullary symbols, or and a negation. Okay. And then take as tree automata, basically the two element Boolean algebra. So you have two states, T and F, true, false, and you take as only accepting state the true state, basically. So you start from your tree and you rewrite, and then you eliminate and you end up with only one state. Okay, so you first replace the constant, which are the leaves. So true, false. Then negation of true of false is true, and then you have true and true, so you have true, basically. Okay. So as you have seen, the example I took is already like a sigma algebra, and it's even more, it was like a Boolean algebra. And this is where you can see some functorial flavor appear, is because if you take a true automaton, it's just a sigma algebra with a distinguished subset. So you have the functorial representation of Lauvier. You take the Lauvier theory of sigma algebra without axioms, so all sigma algebra. And then your first part of your automaton is basically this Lauvier theory. But recall that for Lauvier theory, you ask this functor to be monoidal. Well, I use monoidal, but it's just finite product preserving. And you want to add this out, you want to add the information of the accepting states. So what you do is you force an object out inside your category. So, well, I give a little bit of details, but the idea is just the following theorem. You form out of your Lauvier theory L sigma empty a new category by freely adjoining in a smart manner the object out. It gives you T sigma, like trees, basically. And then true automata over sigma are in bijective correspondence with pointed functor from T sigma to set sending out to omega, such that their restriction to the underlying Lauvier theory is monoidal. So they give a genuine sigma algebra. Okay, so it's not surjective, no, it's kind of injective representation. And application, once again, we can minimize true automata. And I will explain the way we do it in a general manner. All we have seen is automata as functors, and they all look the same. You have kind of a notion of behavior, I. You have a notion of what is output with O. Functors from O to the category in which your automaton lives is D, okay? It was set, rel, intrel, etc. And once you fixed your language, then your automata recognizing your language are extensions. I just add a little detail. An automaton morphism is defined as a natural transformation which restricts to the identity of L when restricted to O. Okay, so it's a morphism of extension, kind of. How do we do minimization? The first step, two steps. The first step is to find initial and terminal automata. And what is actually nice with the functorial framework is that you can get them with can extensions. So you have a systematic way of producing them, basically. Yeah, so the initial one is the left can extension, and the terminal one is the right can extension. You can have other manners of finding those automata, but the goal is inside the category of automata recognizing a given language L, you want an initial and terminal object. Once you have those objects, those automata, what you do is the following. You factorize the unique morphism between the two automata. You get, because so when you factorize pointwise, because you have some epimono factorization system, which is orthogonal, therefore functorial, you obtain a functor once again. And actually, this functor through which the factorization happens is itself an extension of L along the inclusion of O in I. And therefore, you have an automaton. And this automaton is actually a subquotient of any other automaton. And this is why we call it the minimal automaton. In the finite case, it works. It means it's the automaton with the smallest number of states. But in general, it's all the property it have. It is a subquotient of any other L automaton. This is the last slide. We apply this formula to tree automata. So we fix a tree language, so a set of trees. We do this as for the classical case by taking a simple full subcategory S sigma, which plays the role of O sigma star, and bipointed functors correspond exactly to subset of trees. So it's a tree language. And once you choose your tree language, you can see that, but well, you're in set. The categories the category T sigma, sorry, is small, so you can compute the can extension. So both can extension exist, but one subtlety is that the right one is not a true automaton because it does not restrict to a monoidal functor. Okay, but we still have our two L automata, even though they might not be real tree automata. But it's not a problem because you still continue your computing and you can explicitly compute the minimal tree automaton. And in fact, it is a tree automaton because it restricts to a monoidal functor when restricted to L sigma empty. Therefore, you have you recover the tree minimization basically, and well, that was my, I don't know, I think I went a little bit too far. So thank you for listening. I have a few references and yeah.
All right, thank you very much. Okay, there's time for some questions or comments. Anyone has questions?
I have many questions, but unfortunately I have to run, but I'll get in contact with you, Victor. Thank you very much for the call.
Thank you for listening.
I have to head off real soon. Thank you so much.
Okay. See you. With pleasure.
Thank you, everybody, and thanks for the opportunity. Talk to you guys later.
Thank you for talking. Oops, somebody. Wait. Okay. Slightly, there's a question in the chat that says, slightly disjoint to the automata classes discussed. Are there considerations on applying this framework to problems such as automata synchronization?
That's a good question. I actually don't know if someone has looked at it. I'm sorry, I'm not really sure. Also, I have to mention that I am a mathematician at the beginning, so maybe there are some concepts that are still hard to me to grasp. And for example, I'm not sure how like algorithm works well with this setting. You can prove algorithm basically. I think that was the goal of Thomas and Daniela, but like. Yeah, well, and after that with Quentin Aristote, they worked on learning learning algorithm for automata like the L-star algorithm, stuff like that. But yeah, I guess I'm not the I can't say much more about that.